Okay. Okay. So we'd got up to talking about different kinds of shocks, fast and slow, and I'd said that most of the shocks in the heliosphere, most of the shocks that you encounter would be fast mode, where the density increases and the magnetic field increases together in phase. Slow shocks are associated with reconnection outflows. So there are observations of slow shocks in the heliosphere, but to tell you the truth, there aren't that many observations, and there probably aren't that many slow shocks. Okay, so now we just want to talk about a little bit more about shock structure and how it's related to the parameters that we use to describe a shock. And I've already mentioned the magnetic geometry as being really important, and usually that's described by this angle, which we call theta Bn. So theta Bn. So it's the angle between the magnetic field B and the normal to the shock surface N, theta Bn. So if theta Bn is large, close to 90 degrees, we call the shock a quasi-perpendicular shock, such as this shock over here. This is a quasi-perpendicular, so theta Bn is large. If theta Bn is small, we call the shock a quasi-parallel shock. And you'll see that I've drawn in large red lines here what I call them, squiggles. I've drawn some curves which correspond to, in some cartoonish kind of way, correspond to what particles do in those magnetic fields. So if you think of a particle with gyration, then if we put the magnetic field nearly perpendicular to the shock normal, then a particle which is traveling away from the shock, so think about a particle going away from the shock. As the particle goes away from the shock, its motion is perpendicular to the magnetic field. And so the gyration of the particle will bring it back towards the shock. So for a quasi-perpendicular shock, gyration tends to bring the particle back to the shock. On the other hand, in the quasi-parallel shock, if we try and think about a particle with a velocity away from the shock, now the gyration, it takes it around the magnetic field, but the magnetic field is also pointing away from the shock. So the gyration is less likely. Well, let's say the gyration doesn't bring the particle back towards the shock. In fact, the particle can now go away from the shock, escape from the shock. So this magnetic geometry, which we found to be really important, which we find important in the MHD conservation equations as well, is also important in terms of particle trajectories. Okay, the charged particle trajectories, what gyration does to the particles. Now we've got lots of parameters to describe it. We've got shock normal angle. We've got Mach number. So the Mach number is a way of describing how strong the shock is. If we've got a fast mode shock, if it is a shock, it has to have a fast mode Mach number greater than 1. So the flow speed has to be greater than the fast speed in front of the shock upstream. In fact, it's the normal flow speed. So we only think about the flow speed normal to the shock. If you think about it, any other component we can transform away by choosing a suitable frame. So only the normal component of the velocity counts in the Mach number, and actually only the normal component of the fast mode speed as well. So fast mode speed varies as angle, and you have to take that into account in the fast mode shock. The alphane Mach number is a convenient way of saying is it a strong shock or is it a weak shock. Okay. Of course, you've got other plasma parameters, plasma beta, composition, temperature, anisotropy, and so on. So you've got all of these things which affect the kind of shock you have and the shock conservation relations. I just want to demonstrate how we use the shock conservation relations and how we can find out things about shocks just using the shock conservation relations. So we take an example of the exactly parallel shock. And if we then choose, so this is a shock where the upstream field is directed in the normal direction, and there is 0 tangential component. And if we use the transverse momentum equation, which we've written up here, then what we actually find is that this quantity in brackets here, it just becomes constant. If you remember, we've got the, from the divergence component, we've got that the normal component of the magnetic field is constant from div b equals 0. And so this actually means that the change in the transverse field is 0. So we actually find that this component here is constant, and therefore the square brackets around the BT version is 0. And so therefore the change in the transverse magnetic field is 0. But on the other hand, for an exactly parallel shock, the tangential magnetic field is 0 upstream, and so it's got to be 0 downstream. So that means that we don't change the magnetic field at all. So the parallel shock is actually very strange, because this is actually telling us that the magnetic field doesn't change at that shock. In other words, it's just like an ordinary sonic or acoustic shock. That's not quite right. It's still got to do something with the magnetic field, but in terms of these conservation equations, it looks like an ordinary sonic shock or an ordinary gas dynamic shock. You can do other things with the shock conservation relations. For example, if you go to another limit in the geometry and you go to the exactly perpendicular shock, from the conservation of tangential electric fields, you can get this relationship between the upstream normal velocity times the tangential upstream field relative to the downstream quantities. And you can also, and using this, you can also show that the, where are we? That the magnetic field compresses as much as the density. So for an exactly perpendicular shock, the change in the magnetic field is the same as ratio, is same as the density, the change in the density ratio. So magnetic field and density change in the same point. Finally, and this is kind of one of the exercises one of the things that you can look at in the exercise sheet, is that the compression ratio for high Mach number actually tends to a limit, which is just this fraction here, gamma plus 1 divided by gamma minus 1, and if you put gamma equals 5/3, that's just a compression ratio of 4. So in the high Mach number limit, the compression actually tends to a finite value of 4. So in other words, however strong your shock is, the density only increases by a factor of 4. And also the magnetic field only increases by a factor of 4. And that becomes very important, because when you want to sort of generalize to all different kinds of shocks, you've got this very powerful constraint. Yes.
What you're doing is you're pressing as you go, as the speed changes by that amount, then so must the field
and the density. That's right. Okay. Yeah. That's right. For the exactly perpendicular shock. Okay. But as you go to oblique, it changes a bit, but you still find a limit. Yeah. And what is a strong shock? A strong shock has a Mach number of. It's not like a Mach number of 100. It's more like a Mach number of 5 or 6 or something. So actually, the Earth's bow shock, which has a typical Mach number between 5 and 10, this would be counted as a strong shock.
So what is the largest shock that has been observed?
It's probably one measured by you. So the alphane velocity falls off as you go further out in the heliosphere. The solar wind speed is about constant, and so as you go out to the outer planets, the Mach number of the shock is higher. So you go to Jupiter, and the Mach number can be 20, 30, 50, and higher in certain conditions. And you keep going. You keep going. And, well, then I was sort of saying there that the Mach number there depends on how you count the energetic particles.
So the big question is, my shock higher Mach number than your shock?
Okay, we'll avoid the kids at the back squabbling. And I'm, you know, there are several things here, and I'm going to have to skip some things. But there's an important issue about something called the Hoffman-Teller frame. It's this idea that by a suitable frame transformation, which keeps the shock stationary, so the shock is still stationary, it's a frame transformation along the shock surface, which makes the upstream flow parallel to the magnetic field. And in that situation, the motional electric field, which is this minus V cross B, is 0. So we can transform into a frame in which the electric field, motional electric field, is 0. And that becomes very useful when we're considering conservation of energy. So I've shown some details here. It's best shown in this vector diagram in velocity space. So what we have here is a velocity space representation for the shock. And so we've got, if we have a flow in this direction, this is what we call a normal incident flow. So this is a flow which is, you know, we have the shock surface and we have the flow just directed along the normal. If we then transform into a frame which is sliding along the shock at the right speed, obviously there's an aberration in the flow, and we can make that aberration in the flow just point along the magnetic field. So if we move into a frame with this as the origin, then the flow is along the magnetic field. And in that frame, energy of particles is constant because there's no motional electric field. And so if we draw a circle centered on the origin in the Hoffman-Teller frame, it's called, then this circle, or actually it's a sphere, of course, this circle represents the locus of constant energy. So if we want to think about particle conservation of particle energy, the Hoffman-Teller frame is the frame in which you should be working. So you often find references to the Hoffman-Teller frame, or the de Hoffman-Teller frame. We're a little bit sloppy. We often call it the Hoffman-Teller frame, but his name was de Hoffman. So it should really be the de Hoffman-Teller frame. Okay, so as I've said, that we've got this very important distinction between quasi-parallel and quasi-perpendicular, which turns up in the conservation relations, but it also turns up in the kinds of particle trajectories. And the kinds of particle trajectories that you get at a shock influences the structure that we see in the shock. I was talking about the collisionless shock, there has to be some interaction between particles and electromagnetic fields in order to essentially allow that near, discontinuity-like solution. And it turns out that the distinction between quasi-parallel and quasi-perpendicular is actually also seen in the structure, in the kind of magnetic field we see. And so in the quasi-perpendicular shock, and this is an example here, this is actually closest to the idea of a discontinuity. When you look at it, there is a fairly abrupt transition from an upstream with low density. Density increases fairly sharply, and then there's a downstream value of increased density. So the quasi-perpendicular shock corresponds most to the discontinuity solution, and it corresponds to this situation where particles are gyrating and returning to the shock. Actually, when you look in detail, there's structure in the magnetic field and density associated with that reflection. So it actually turns out that there are some particles which actually bounce at the shock, turn around their velocity, and start going in the opposite direction and gyrating upstream. But their gyration brings them back to the shock. The quasi-parallel shock, on the other hand, and this is a little example, I'm just, basically I just want to get the story across to you that this is noisy, this is messy, it's turbulent. Quasi-parallel shocks are at high Mach number are generally very turbulent, very messy. It's very difficult to analyze them in terms of exactly what's going on. On the other hand, at some large scale, we still see a transition from upstream. The density is low, and then the density is high. But in between, it goes high, and then it goes low. And we find lots of different kinds of waves, very large amplitude waves. Delta B divided by the B0 can be order of 5, 10, 15. So these are very large amplitude waves, very intense turbulence. And these are associated with this kind of particle trajectory. So if you reflect a particle, then it tries to go upstream. And then in the upstream, it can generate waves. So actually, all these waves and turbulence are a signature of instabilities, plasma instabilities, and so on. As I said, the quasi-perpendicular, we can actually follow the story quite nicely. We can actually have observations of particles measured right inside the shock, where we see reflection of particles from the shock and this gyration. And if we look at a schematic, then we have a picture like this, where there are some particles in the solar wind distribution which come in, hit the shock, and actually get reflected. They change their direction of motion, and their gyration takes them around, and they gain a large perpendicular velocity. That large perpendicular velocity is actually the heating of the proton distribution that we need to have to satisfy the conservation equations. There's an increase in pressure across the shock, increase in temperature, and that reflection provides that heating. So there are also some particles which go straight through. They don't contribute so much to the heating. So we've got this rather interesting thing that this is how, just giving a little bit of insight into how a collision-less shock can actually produce heating at a very short, abrupt discontinuity. It does it by tearing apart the velocity distribution. So as the velocity distribution comes in the solar wind, some of it is actually reflected, and the particles gyrate around. They gain a lot of perpendicular velocity. That perpendicular velocity corresponds to energy. There's some scattering, and you get perpendicular heating, which then isotropizes, but you get heating. So the reflection produces heating. And so that's really an insight into how you can have a collision-less process producing the heating that you need to have to produce this transition on a short scaling. Strangely enough, even though the quasi-parallel shock is very, very messy, lots of very large amplitude waves, very difficult to analyze, you have large problems with the observations because particle instruments usually only take 5 seconds or so to take a measurement, but we need to have observations here being taken at 1/10 of a second, and we don't have those observations yet. So that it's very difficult to analyze here, but actually it turns out that the same sorts of processes of reflection, tearing apart the distribution function and sending particles on different kinds of trajectories, that's also happening here. And you find these very large, very short-lived magnetic pulsations where the field will increase by a factor of 5 or 10 over the local value, and it's all very small scale. So I just wanted to sort of point out that we have some insight into those collision-less processes. Okay, I'm not going to show you any movies. There's lots of movies that can be shown of simulations of these things. A lot of what I've already told you is based on looking in detail at what happens in simulations. So this whole knowledge, this whole area of knowledge has built up by looking at observations and then going to simulations and seeing if the simulations can explain the observation. So there's been a lot of interplay between these two things. I've got a low battery. I've got 10% on my battery. Oh, well, we'll see how long it goes. Okay, so now what I want to talk about is particle acceleration, and I hope I've got about 25 minutes left.
Can't you hear?
I don't know. This is just the tablet. That's the presenter's tablet. Yeah, it's probably okay. Yeah. Well, it'll be one way that I don't go on too long. Joe has set a very bad example. Okay, so now I want to sort of move on and talk about particle acceleration at shocks. And the whole point really is, it's in a collisionless plasma, you can have the situation that a small number of particles gain a large energy. So we've got this picture that everything that we know about shock physics is okay. That we know about conservation equations. We start using simulations to understand the structure, and then within those changes in the field, we say, now let's see, can some small fraction of the particles gain energy? And essentially, that we have to remember where that energy is going to come from. The energy in the end is going to come from the fact that at a shock, we have a compression. The flow slows. So really, there is already there's a lot of kinetic energy in the flow, which has to be dissipated. So that if you take a little bit of that energy and put it into high energy particles, that's all that we need to explain the energetic particles we see. The compression is one way. That's a sort of gas dynamic way of thinking about where the energy is coming from. You can also think of it as like frame transformations. There's this from this velocity difference. If I can couple particles to the velocity difference, then I'll also be able to give them some energy. And that's one of the questions in the homework. Another way of thinking about it is that in the shock frame, there is an upstream flow, and there we have this motional electric field. And it's actually that the transverse component of that motional electric field is constant across the shock. So if I've got a way of making particles drift in the direction of the motional electric field at the shock, then they're going to gain energy. Okay? So they gain energy from the electric field. And they gain energy from the electric field because the shock, the shock itself is holding them at the shock in some way. So if there's some forces at the shock which can hold a particle at the shock, then the particle and the particle drifts in the right direction, it'll gain energy. So yeah, these are all different ways of looking at where that energy comes from. Okay, and they're all related, and in the end they boil down to the same thing. Yeah. Yeah. So, are you talking about particles losing energy to waves? Yeah. So damping. Yes, you can have waves, and they can absorb energy from the particles. Okay. So then you get wave. Yes, that's right. So you can also have waves which give energy to particles. Yeah. And the point is that in the shock, where you've got these strong gradients in the fields, that then it's the interaction between the particles and the fields within those gradients which allow us to get particle acceleration. Yeah, I mean, it's not exactly the same. I mean, but the idea of transferring energy from electromagnetic fields to particles is the same. Okay, but the mechanisms are not always the same. Okay, not always the same. I mean, for example, sometimes it's a cyclotron interaction instead of a Landau interaction. Okay. Okay. Okay, so I just wanted to now use, again, the bow shock to talk about energetic particles. And I'm just going to go across the bow shock and talk about some of the mechanisms that can be used to explain the energization. And you can use these mechanisms in other areas, okay? So it's not, these are all sort of mechanisms which will work in other places. So we've got this observations of the energetic electrons, and this is, right at the edge of the foreshock, we see energies up to several keV or tens of keV. These happen right at the foreshock edge. And this corresponds to the quasi-perpendicular shock, as I said. So the tangent field line is connected to the perpendicular shock. That's just showing you that. And the mechanism which has been used to explain this acceleration is actually directly related to the idea of coupling the change in speeds across the shock. So you've got the shock and you've got an upstream flow. So if you can imagine a particle which comes into this shock in the upstream frame, the shock is moving along the field lines. Okay. So in the upstream frame, the shock is moving. So it's all frames, frame transformations. So we're not thinking about the shock frame where the shock is stationary. We now think about the upstream frame, and the shock is moving along the field lines. So as the shock moves along the field lines, if the particle bounces off the shock, then it's going to gain energy. Just in the same way as a ping pong ball and the bat, you bounce the ball that gains energy. So how can we take a particle and make it bounce from a shock? Well, a fast mode shock has an increase in the magnetic field. So we can think about the magnetic mirror force. So if a particle mirrors in the field increase of the shock, then it can gain energy. And this is exactly the mechanism that's been suggested for these energetic electrons in the Earth's foreshock. Where we leak from downstream to upstream. Yes, there is. I'll mention that in a second. Remind me at the end. So here, what one can do is one can essentially follow through a process of deciding which particles are going to reflect according to their magnetic moment and pitch angle. And essentially what one does is one uses Liouville's theorem to map the upstream distribution function and then find out which of those particles are reflected at the shock. And in that reflection, they gain energy. And what you can do is you can follow through this process. Let me just use this cartoon. So this is the cartoon which shows the Hoffman teleframe. And if you remember, in the Hoffman teleframe, energy is conserved. And it's also in the Hoffman teleframe, where there's no electric field, that we're going to conserve magnetic moment. So this point here is the origin in the Hoffman teleframe. This is our incident flow. This is one contour in the instant flow. And we've put on some conditions for magnetic mirroring. So the pitch angle has got to be larger than a certain amount in order to magnetic mirror. And so there is a small fraction of this contour here and here, which will correspond to mirrored particles. That mirroring simply reverses the parallel component of velocity in the Hoffman teleframe, where there's no confusing electric field. So these parts of the contour are flipped around to here, to the opposite parallel velocity. And you can now see that if I look at the energy in the lab frame, in our normal instance frame, which is this origin here, then we actually see particles which move in velocity space from here to here. In other words, they gain a large amount of energy. Okay? So that's why the Hoffman teleframe is so important, because it allows us to take this idea of going into a frame where the energy is constant, doing some transformation of velocity, which is straightforward, and then as we go back to the lab frame, or the normal instant frame, or the shock frame, then we can see that this corresponds to energy gain. So this would also sort of predict, of course, beams of energetic particles, and one can see. Now, for the electrons, the gyro radius is very small. It's smaller than the width of the shock, and so that whole idea of conservation of magnetic moment is a good approximation. Now, it also turns out, if you remember, I said that there were these beams of protons, so not electrons, protons, which are also seen at the Earth's foreshock. And this is observations of what the velocity distribution looks like of these field-aligned beams, they're called. And in this case, you can also use a similar idea of reflection to explain the energy increase. So they're being reflected at the shock. But in this case, the gyro radius of the protons is much larger. In fact, it's larger than the width of the shock. So we can't really use the assumption of conservation of magnetic moment for the protons. But it turns out that in this case, there is a related mechanism that also operates to give them energy. And this is what's known as shock drift acceleration. And it turns out that, for some, if you start off with particles which have got a certain energy, they're not completely low energy, they're sort of mild energy. And as they interact with the shock, and this is a picture of one particle interacting with the shock, its gyration is sort of caught on the shock. It catches on the shock for some time. And it actually drifts along the shock surface, hence the name shock drift acceleration. It drifts along the shock surface in the direction of the motional electric field. And so it actually gains energy. Now, why do we have this drift? Well, it's related to the gradient B drift. So the gradient B drift, if you remember, or you might not realize, but the gradient B drift is if you've got a change in the magnetic field, that change in the magnetic field changes the gyro radius. So on one side, the gyro radius is small. On the other side, the gyro radius is large. You put those two parts of the trajectory together, and you actually get a drift. And that gradient B drift is in the right sense for protons to pick up energy from the motional electric field in the shock frame. So the shock kind of says, okay, proton, you're going to stay in my frame for a while, and if you're in my frame, you're going to have to do a drift, and you're going to gain energy. Now, once it's gained enough energy, it might not stay in the shock anymore, okay? So it's only going to stay, it's not trapped forever, but it does gain energy. And this mechanism, shock drift acceleration mechanism, is associated with sometimes what are known as shock spike events at interplanetary shocks. So some interplanetary shocks, you have an increase in the energetic particles, which is very highly localized to the shock transition. And that's an example on the right here, where you've got this increase in the energetic particles, and the dashed line here is where the passage of the shock was seen. So finally, in terms of different kinds of mechanism, we have to think about how these diffuse ions are created. So these are particles which are seen associated with the quasi-parallel shock, where we have a lot more waves, turbulence. We've already mentioned, Joe has already mentioned the idea of scattering of particles in the electric and magnetic fields. And we find an almost isotropic distribution. This is in energy distribution, this starts at perhaps 5 keV and goes up to several hundred keV. So it's not cosmic ray energies, it's kind of intermediate energies. But it's isotropic, which kind of reminds you of what's happening for cosmic rays, that they were isotropic, and the argument that they were isotropic was that there's a lot of scattering. So it looks as though these particles are actually being accelerated because of scattering. And here, this is just the spectra. And one of the pieces of evidence for scattering is that if there is scattering, then the particles should be diffusing. And there's actually evidence from cluster spacecraft where what they did is that there's one certain passage of the foreshock where you could actually look at the profile of the energetic particles as you got closer to the shock. And you essentially end up with a particle density if you take two spacecraft at a certain distance away from each other, you can look at the relative magnitude of the particle intensity, and you can actually work out that the fall-off in density just corresponds to the exponential fall-off that you would expect from diffusion. So if you've just got a source of energetic particles at the shock and you just let them diffuse into the upstream flow, then you get this exponential fall-off. And this is the evidence for that, and you can find that there's some characteristic length scale for that fall-off. So as it says there, that this is a strong indication that we have diffusion going on for these energetic particles. And this goes back, again, this now begins to link up with some of the things that Joe was talking about, because there's a whole big theory that I'm not going to have much time to talk about, called diffusive shock acceleration, which essentially is the studying acceleration by looking at the evolution of the distribution function with the ingredients of the slowdown in the flow. So this change from fast upstream flow to slow downstream flow, this delta V, the change in speed, the compression across the shock, plus scattering, so you need to have waves, and that scattering produces diffusion. So we've got a combination of compression in the flow and diffusion, which allows the energetic particles, by traveling upstream to downstream, to upstream to downstream, of sampling that compression. And if they sample the compression, they gain energy. I'm not going to spend too long on this. Some of these things, already mentioned, the Parker transport equation. You've got these different terms. You're putting together convection, diffusion, energy change. The source term corresponds to some process which is injecting particles out of the thermal distribution at low energy and just starting them off. And then once they start off, they can start this diffusion process. It turns out that for the diffusive acceleration, that if you take an ideal one-dimensional shock and you look for a time-steady solution, so you let time go to infinity, you actually end up with, and for strong shocks, where you've got this, for strong shocks, you've got a density compression ratio which is limited by the Rankine-Hugoniot relationships to a factor of 4. It turns out that you actually get a power law for the energetic particle spectrum, and that this is a universal power law. And so diffusive acceleration theory is, so that's why the same theory that's been used to explain the diffuse particles at the Earth's bow shock or in front of a parallel interplanetary shock, that's also been that's also used to explain cosmic ray acceleration at supernova remnant shocks. So it's a really powerful theory. For the bow shock, we have to modify it slightly because we don't actually see power law distributions, and that's really because the Earth's bow shock is very small, and so it's time dependent. So it gets more complicated. That's in the notes. I'm going to skip over that a little bit since it's not all that important. Right, this is just showing that if you put on time development, you end up with actually an exponential spectra rather than a power law. I should say also that one of the interesting things about this whole area, I want to sort of emphasize that you've got the fact that simulations are used so much now in shock physics to understand what's going on. It's very difficult because of the very strong gradients and the very strong gradients and the large amplitude turbulence that you get. It's very difficult to study this completely analytically. And so one can do these very large simulations of acceleration. This one's by Joe, and actually here we have got the magnetic field and so on, and the change of density and so forth. And this is the energetic particles. And also, if you look at the spectrum, you can begin to see this transition to a power law. And then above a certain energy, because the whole simulation is finite in time, and in this case finite in distance, you get a high energy cutoff associated with the finite size. So there's a link between the size of the shock and the maximum energy you can get. There's another interesting thing which has been discovered in these simulations, which has really changed our view of diffusive acceleration theory, because I mentioned that in diffusive acceleration theory, there's this idea that you're coupling the downstream, the upstream and the downstream flows, so the fast flow and the slow flow, this density, this velocity change. And you were coupling by having a particle which goes downstream, and then it goes upstream, and then it goes downstream. So that particle, the energetic particle, had to go upstream and downstream. In the simulations, and this is some other work by Sugiyama, and the reason I'm showing this is it actually shows you here a particle trajectory in distance and energy. So this is a particle which comes along here at low energy, and it hits the shock, and it starts to increase in energy. And that increase in energy happens right at the shock. It then starts to escape upstream and goes upstream, and then it diffuses, it scatters in the upstream waves, and it starts coming back towards the shock again. In this case, it does go downstream again, but then it gets back upstream again. And when it gets back to the shock again, it increases energy again in another step. And then it goes upstream, back down to the shock, straight up in energy. It doesn't go downstream. So it's actually turning out that from these simulations over the last few years that really the picture of an energetic particle going downstream, upstream, downstream is not really right. It really looks as though what's happening is it's the interaction between the upstream and the shock which is most important. So the particles which are going, they come into the shock, they gain energy, they go upstream, they come back to the shock, they gain energy again, and then they go upstream. So we still have this compression between the upstream flow and the shock itself. So there's still a compression going on, but the particles itself aren't sampling the downstream. So this is where simulations have really given us an insight into what we already knew about, what we knew from theory. I mean, it's not really my area, but there is an enormous amount of work which has been done recently on modeling real shock events and comparing with observations, especially for the space weather aspects. And so I just wanted to point out that this is not an easy task, because one of the problems is that it's a big three-dimensional task. When we see a particle at a spacecraft, it depends on its energy, it depends on the field lines it was traveling on, it depends when it was accelerated, where it was accelerated. All of that, it has to be folded together. And so if we take an event where we've got a CME and we have a shock around a CME and we have accelerated particles, these particles can be accelerated all around the shock. But the shock is different at different places. Sometimes it's quasi-perpendicular, sometimes it's quasi-parallel. Not only that, but as the shock expands, first of all, it expands rapidly and it's small, and then it expands more slowly, but it's large. So there are all these different factors which have to be taken into account. And that difference is also seen in the observations, where you see a lot of difference in the kinds of profile of the energetic particles. Sometimes you see these shock spike events I've already mentioned. Sometimes you see long-lived events which might be associated with a quasi-parallel shock. Sometimes you see an increase which actually doesn't correspond to where the shock was crossed. So how is this all put together? And of course now in the current era, where we have several spacecraft spread across the heliosphere or the inner heliosphere, with stereo and ACE and so on, we can actually look at the energetic particles for the same CME at different locations. Okay, so we don't even have to do statistics. We can just take a single CME and look and see how we get different energetic particle profiles. And you can see in this example how this profile of energetic particles is different from this one. So how does it all put together? It's put together by trying to do simulations which include a shock wave, which is, in this example here, which is by Aran, 2007, and the group in Barcelona and others, of where you have a shock wave, which is modeled as an MHD shock wave expanding in the solar wind, and then you use particle tracing to say where did the particles come from, what shock did they come from, and then you have got some mechanism for the acceleration of those particles. And if you do that, then you end up with this, which hopefully will or will not run. Oh, talk to me. This was a GIF. Even GIFs, even animated GIFs. Oh, that's a shame. That's a shame. That's a shame. Okay, right. So let me just so you'll have to go on the web and look for this. But the idea is that what you can see is in this picture here, that as we start with a very small shock here and we have an observation point here, that at early times we have very fast energetic particles which we'll see generated on one side of the shock, and at later times we'll be seeing particles which come from a different portion of the shock, where because the shock has expanded, it's become weaker and it's become a different kind of shock. So all of those different factors have to be taken into account in this realistic modeling. Okay, fine. So as I said, I'm sorry about that the movie doesn't work. That's a shame. But I'll put that up. So I'm going to finish there, but that I just wanted to make sure that you can download. If you look at the session and the files in the session, there's a file called Shocks Chapter PDF. So if you just go out of presentation and you go to the session, you should be able to download a PDF file called Shocks Chapter, and there's also a PDF of the presentation, because some people said that the presentations, they couldn't get hold of them from the Millennium Hotel. So I've actually made a PDF of the presentation, which is also in the session. Can people see those files? Okay, so if you want to download them, you can do that now, before the session ends and everything is destroyed. It's ended. Okay. There's ice cream out there for you. Why did you let me carry on? Okay, I've handed out some coursework. As I've said at the top, I gave lots of questions because I'm just really interested in my own subject. But really, if you can just have a look at the questions I've marked as the ones that I'm going to go through. I'm only going to go through questions 2 and 3. Okay? So just concentrate on those. If you want to just look at the other ones and ask me questions, then feel free. Later in the week. Okay, thank you.